Okay, it's another update of the lovely fusion reactor, aka wet, hot, steamy fusion. So this is a breakout of what's going to go on. Okay, we'll start again. This is the main fusion reactor. Wet. I've got dry gas and wet gas. So both gases come out of here. They get split into a drying agent. Then the wet is metered here through this flow meter. The dry is for this flow meter. So I'll show you what I'm talking about. I'm going to turn on the gross valve. And adjust the give me a second. There we go. I had the valve all the way closed. It's very sensitive. Okay. So now we can balance the gases between wet and dry. You see that? See how just when the light one goes up, when you have it in the sweet spot, the light gas goes up, but it's pulling the heavy gas up. Well, how can that be? Because that's contrary to Einstein's mass. No. It's what's inside of here. The Venturi effect inside of here is pulling more CFM than it's using. It's something that I patented back in 1998, 97, somewhere around there. It's a peculiar vacuum Venturi. You see that? The light ball definitely is lifting the heavy ball. Now watch, I'll get it out of the sweet spot. Here. Take it out of the sweet spot. There we go. Okay. There we go. Does not want to come out of the sweet spot because the pressure is low. That just taught me something. Okay. It's kind of what I figured. But it taught me something. Because when I had it up at 25-30 psi, they were contrary. Because the cavitation effect inside the Venturi. So right now, the Venturi can pull down to there, which is even better than I expected. So it definitely taught me something. There we go. Now, we're past the sweet spot again. And even if the light ball goes up, the heavy ball won't lift. There's a sweet spot in vacuum, and that's kind of why I put these gauges, so that I can balance between the heavy gas and the light gas to get a, maybe I want a stoichiometric matrix, maybe I want a perfect balance, but maybe I want an imbalance depending on the pressures at play. Okay. So this is Steamy. This is just a basic representation of what I'm talking about. It's a gradient heat directly to electricity. It's a fuel cell that I developed. It works phenomenally well. But if you change the gradient on the outside from ambient to something else, cooling water or whatever, heat your bathtub, heat your swimming pool, whatever you want to do, you can still use that gradient of water. So instead of letting it go to the atmosphere, might as well just use it, which is very much contrary to how a power plant works. A power plant spends most of the property and most of the equipment trying to get the steam back to water. So they waste that energy and they don't know what to do with it. It's thousands of degrees. It's about 900 degrees. It's not really thousands. It's about 900 degrees of just completely wasted energy after the steam turbine. So we don't need a steam turbine in fusion energy, not when you have Steamy, because the phenomenon about Steamy in the fuel cell that I brought, in 1 foot of, I made a fuel cell specifically 1 foot long, so I had the same exact surface area as the solid oxide fuel cell, my competition from heat to electricity. But they need 1800 degrees of temperature to go to make electricity, and a gradient of 350 degrees exhaust up on top of ambient. And they better not have any kind of contamination in the air going into the fuel cell, or they clog. They're very sensitive, and they start up and they crack, and they're just tremendously expensive. This is a very inexpensive, and the catalyst, all the catalyst for my fusion reaction, they're all in situ. That means we're not beholden to anybody to buy specialty catalyst. Okay. And in fact, while we're on the catalyst subject, I'll just be right back. So this is our machine shop, but pardon the little bit of a mess because I've been working. Okay, so there's our boron for our deuterium fusion reaction. Borax, okay? $6 for a box. It'll last you a lifetime. If this was an expensive endeavor, I wouldn't do it. If you were beholden to some chemical company that could extort you for some exotic palladium electrode or ridiculous stuff, I wouldn't even entertain this. This is affordable. And that's the magic of fusion. When it's done right, everything is affordable. From the basic understanding of the reactor to the catalysts that I use, I either grow them in situ with specific frequencies, so there's some proprietariness to there, so I can control what goes out there on the market, and under process secrets of Coca-Cola, trade secrets. You're not going to know my recipes. You're not going to know my ambience. You're not going to know my pressures. You're not going to know my temperatures. You're not going to know my mixtures or when to add the ingredients, any of that stuff. Just like Coca-Cola, because it's too dangerous. It's pointless, actually, because when you have the reactor, it's a catalyst. It's the version of the definition of a catalyst. It's there forever. Your makeup water is whatever you want. You can use seawater. You can use dirty water. You can use distilled water. You can use rainwater. You can use tap water. It doesn't matter what the makeup water is. It literally does not matter. It doesn't even matter what the hell's in the water. It's gone. It's all reduced back to hydrogen. Everything and all the chemicals that were in the water, everything are completely removed back to what they either what they should be, or they enhance the catalyst. That's the magic of the catalyst. It's so strong and so powerful, the fuel mixture that I made, that there's nothing that you can put in there that it will not bring it back to the ground state. So that's the beauty of this whole situation. And the frequencies that are imposed during the fusion reaction control that, because they're ripping the elements apart on a gravitational pull. You cannot upset that. And that's the irony of why, number one, the ITAR reactors and all that stuff, they're never going to self-run. That's just an absolute waste of money, because the bigger they think they get, the bigger they think that they can make it, the better it's going to be. Well, that's wrong. It's 100% wrong, because they have to defeat gravity. That's the problem. And because they're completely wound, those magnets are completely finished, those power supplies are completely done, they would have to completely rip that whole thing apart and build it my way. It's junk. It's a big donut. You might as well cement the inside of it and make a half pipe for skateboarding in it, and bicycles and motorcycles. That's pretty. You'll make more money out of that thing than you will throwing your money in that toilet hole. Okay? Because you're never going to get bigger than the Earth. The Earth you would have to effectively make the ITAR reactor around the equator, and then half of that would have to be half the mass of the Earth. And then Earth would still kill you, because it's already a fusion reactor inside. It's just not, it's physically, it's not chemically, it's not scientifically, it's physically impossible. The math is all there because it's here. Okay? For the number one reason, I'm using my energy platform and my way of doing it. And you don't see any coils here. You don't see any trying to... The ITAR reactor, to think that they can self-run, they are using 500 million amps and 14,000 atmospheres. Okay, it's the bottom of the Marianas Trench in pressure in the Tesla, in those superconductive magnets, to go. It's wrong. They're just doing it wrong, and it's not their fault. They're just parroting somebody else's parrot. And the person who, I can't even remember his name, I watched his personal interview on his deathbed. He said, I'm not going to work. I engineered it. We already got funding, but I'm telling you, it's not going to work. Okay, well, why isn't it? Well, I can tell you why. He doesn't. If he knew why it didn't work, he would tell you. He's just telling you it's not going to work. I'm telling you why it's not going to work. So let's move to the next thing. Ultimately, in the four-phase superconductive grid system, the reactor and the fusion and everything will be in one hot water tank. I'm just breaking it out here so that I can show you the different phases of the fusion and what each phase does. So if we come here to the Divine reactor, this we only need 10 psi. We don't need any more. I can guarantee you. And then will pull vacuum and will balance that load, and you'll see what I'm talking about. You don't need millions of pounds of pressure. That's ridiculous. If I put their joules into one of my reactors, I would put the sun out. It would be ridiculous how much energy you could get out of it. It's linear for a reason. Yes, you can definitely scale this up. There's no question. But if you cannot do it here, what's the point? Okay? There is no point. If you can't properly do it in a very simplified manner, then there is no point. Okay? I've already built bigger systems and torn them apart. The reason I'm not video them or unlocked them from YouTube is because they're messy. The experiments, I don't care what the wiring looks like. I don't care where my tools are at. It's just documentation for me and a date stamp for the patents. That's it. That's all YouTube is really for me. That's it. That's why you don't see very many views on videos that were 7 or 8 years old, is because I just turn them on to get the date stamp, and then I just keep them to myself so that when I come back to this patent disclosure on Fusion, I can reference those. Maybe I'll unlock some of them that are interesting, but most of them, it's not important. So you'll see new built reactors that are mice. This is specifically set up so that I can take it someplace. I can go to Tesla Technology Conference. I can go to venture capitalist meetings. I can take the stuff and show that it works, because it's nice to have a video and, you know, this for reference and update. But don't you want to see something in person? I do. I want to touch it and feel it. I want to twist the knobs. I want to see all the power supplies. I want to see all the meters. I want to make my own decisions. And that's what the world has been waiting for, is somebody to show something instead of just talking about it. So let's move on. So this is a recirculation pump. It's just an air compressor pump, right? But it just has reed valves in it because it's not really compressing water. It's going to be moving hot steam. Then it's going to, the aerated steam will have a compression point because it'll have bubbles in it, nanobubbles. And that's very important to understand what a nanobubble and how it works off of vacuum, okay? To properly produce a nanoscale bubble to infuse the hydrogen in the bubble. It does it off the electrode automatically, but this does it for a reason, so that we can get the water as dense as we possibly can with hydrogen. And it raises the pH dramatically, okay? This is how we get 33 pH, because we're pulling 40.8 inches of mercury to do this. This both, you saw the earlier video where I had 9 vacuum Venturi jets. That is for something else. This is where all we need for here. So there's 1, 2, 3 Venturis, and that's it. That's all we need. The expansion chamber, the primary Venturi, this is where the massive amount of vacuum comes from. And that will come in to the reactor here. And it's just open. I have no valve on this one for a reason. Because if I want to put pressure in this reactor, then I'm putting pressure in these 2 lines. This line is the out. This line is the in. And they'll come through the Steamy reactor. But what the Steamy does is it takes the empathy, not necessarily the temperature, which is phenomenal, but it takes the empathy from the steam and it condenses it down to water in 1 foot of pipe. I can take hot steam in 1 foot of pipe and have liquid water out the other end, which is something that no power plant can do. They use tremendous amount of coolers, a nuclear power plant, a natural gas turbine power plant. They use tremendous amount of cooling to try to get that steam down to water again, because there's no more energy left after a certain point. Okay? That's the hardest thing to do. It's a little easier like on a ship where you've got the ocean, you can have some cooling water and things like that. But when you're on land, it takes a tremendous amount of land to do that. I'll give you an example that you'll see on the Steamy page. The power plant that we're bidding against to tear down is 20 acres of nothing but heat risers and chillers, coolers, to get the heat to drop the water back down to reuse it again. The turbine fits in a room that's only 10 feet, 15 feet wide by maybe 50 feet long with the generator and everything. The rest of the property is just to get rid of the heat. Steamy gets rid of the heat in a very small footprint and turns it directly to electricity. So when the steam, when this temperature here is no more than 500 degrees, okay? It doesn't need to be, because it's a massive amount of energy in just that 500 degrees of deteriorated water. Goes through the reactor and it gets superheated through this reactor. Then it comes back through here through the Steamy, and then once it's finished here and the water has condensated, so we're going to run it up, not down, up, then back down, because I want as much lens effect. We found out something that during the Steamy process, it's definitely the lens effect. So it's going to come up here and then go back down and bubble up through the bottom of the catalyst, closing the empathy cycle from carbon to graphene to carbon to graphene, back and forth. So that answers where energy comes from. It's the movement from carbon at the ground state to graphene to its higher energy state. That's what we answered with this. Technically, what you're looking at is an implosion, explosion of CO2. That's what this is. We've figured out that we can explode CO2. This is why it's closed loop, okay? The same principles apply to the engine that we're building. So far, so it's a messy update. I've got it as far as getting the test connecting rod to the crankshaft. Here's the flywheel. Here's the belt, just because we're hot rodders, might as well use a Jessel belt on that project. But that's a closed engine in the same principles of this cycle. It will run off of this gas, off of this hydrogen gas that comes off of here. So then we have the next step is that the gas, after the CO2 is bound and locked, but the fuel that comes off of here is easily separated to keep the CO2 locked in this chamber. But even the fuel burn, after the exhaust of the fuel burn in a boiler to even superheat, keep the potential of the water even hotter. Yeah, even hotter. Okay, that fuel, we can loop that exhaust right back into the catalyst, because that fuel is the gas of this catalyst. Okay, that's what's badass about the fuel, is that it's a heavy hydrogen deuteride fuel, completely chemically laid out, fits perfectly in all chemical models, all the way down to the Claire's goblet. Okay, so you're going to see in the next update, because I'll be working on this, you're going to see how powerful the deuterium Pure E proprietary fuel that runs this catalyst is up against boron. I just been spoon feeding you guys. Okay? So the boron fusion reaction is the most coveted reaction because it's the hardest to produce, but it has the most potential. All the other ones blow their potential out the door trying to break the electron volt. The boron is down at 8. The tritium and helium are up at the 20, 24 electron volts. That's just ridiculous. It's just wasting. Your empathy's already gone at that point. That's why they do it, because it's easy. That's why they don't get any fuel out of it. They don't get anything because there's nothing there. It's already gone. It takes just as much in as it out of electromagnetism. Even though we've already did those, they're fine. This is the holy grail right here. Boron, deuterium. Well, it's actually not necessarily deuterium. They think it's deuterium. It's actually boron hydrogen deuteride on top of my catalyst, which is, I'll say it again, G for graphene, C for carbon-12, 36. Hydrogen deuteride, 54. O for ozone-7, 74. Au 197M, in situ 11, and number 26. Don't worry about what number 26 is. Okay? There's your update on the lovely, wet, hot, steamy fusion reaction. But I must say one very important thing. This is nowhere near as efficient as just going straight from the linear magnetic power supply to the grid. This is for all of your heat loads, which is ridiculously efficient. It's not necessarily a place to make electricity. I want to make that extremely clear. It's just the fact that we can do it. Might as well. You need to bring the empathy down anyway. Instead of using a chiller and blowing it out to the atmosphere, you might as well just go direct to electricity. We're already 100 to 500 watts in to squared 44,000 watts out, and or 168 amps, 73 amps, depending on wet or dry. But it squares because of ohms between the two at 44,000 watts. That's where we're at. And the reason we're there is because I've purposely left you at linear magnetism, 0, -1. It goes 033 negative, 033 positive, negative negative, positive positive, positive negative, positive negative, negative negative negative, positive positive positive. Okay? Squared heterodyne. It's ridiculous how many frequencies that I can come up with that regular AC and DC does nothing. That's why you're seeing the cakewalk of one electrode that's cherry red hot and the other electrode that's freezing cold. It's relatively warm, but it's definitely not cherry red hot. That's just 1.0. When I go all the way to 33, and we've never mind. Just never mind. Okay, it's not important. That's good enough. Okay. Now you'll know a little bit more of the understanding of this patent disclosure for fusion that I own. Have a good day, and I'll talk to you soon. I got to get back to work.